Assalamualaikum warahmatullahi wabarakatuh to our lecturer, Encik Muhammad Nur Anwar bin Muhammad. My name is Nur Masnira Ajira Binti Dozan. I'll be the first presenter for our project, which is gas turbine in combined cycle power plant. We from Group 4. So in this slide, we have information for my group member, which is consists 5%. So, in this slide, we have the introduction for our project, which is the Combined Cycle Power Plant (CCPP) integrates the Brayton and Rankine cycles to significantly improve thermal efficiency by utilizing waste heat from the gas turbine exhaust to generate steam for additional power production. This setup captures energy that would otherwise be lost, enabling efficiencies exceeding 60% compared to the traditional plant with 33 to 40%. The system's rapid startup capability made it ideal for balancing and fluctuating renewable sources like wind and solar. Thermodynamic analysis of components such as nozzles, compressor and heat exchanger, based on the first law of thermodynamics, explain how each device contributes to overall efficiency and energy transformation within the CCPP. So the next is the objective of our project, which is the first is to analyze Brayton and Rankine cycle interaction in a CCPP using gas turbine fundamentals. The second is to apply first law, which is open system, to 7 key components to evaluate energy balance and power contribution. And the third point is to solve 21 case study focusing on mass flow, enthalpy change, heat, and work transfer. And the next point is to compare isentropic, polytropic, isothermal compression to define compressor efficiency limits. And the last objective for our project is to evaluate two-stage compression with intercooling to reduce work input and improve the net work output. So in this slide, we choose refrigerator, air conditioning, then heat pump because refrigerator is related to our group project. So this is the explanation for refrigerator, which is the first thing we have compression, which is the cycle begin as a low pressure, low temperature, saturated vapor enter the compressor. Through the isentropic compression, the pressure and temperature are significantly increased, turning the fluid into the superheated vapor that is hotter than the outside environment. So the second process is condensation, which is the hot gas flow through the condenser coils, where it undergoes isobaric heat rejection. It releases heat to the external air of water, causing the refrigerant to condense from a gas into the high-pressure liquids. And the third is we have expansion. The liquid passes through an expansion valve or throttling valve, expressing isentropic expansion. The sudden drop in the pressure causes the flash evaporation, which drastically lowers the temperature of refrigerant mixture. And the next point is evaporation, which is the cool liquid vapor mixture enter the evaporator coils. It performs isobaric heat absorption, soaking up the thermal energy from the interior space, cooling it down. This causes the refrigerant to evaporate back into the low pressure vapor. And the last point is efficiency. The cycle effectiveness is measured by the coefficient of performance (COP), calculated as the ratio of cooling energy removed to mechanical work provided by the compressor.
Assalamualaikum and a very good day. My name is Nurul Irina binti Muhammad Akram. My matrix number is CD240184. So here are the problem for choosing device. So from our group project, gas turbine in combined cycle power plant, we choose 6 devices. Let me introduce the first device, nozzle. The functioned gas turbine nozzle in a combined cycle plant convert high pressure combustion gases into a high velocity jets. It expands and accelerates the gases efficiently, directing maximum impulse into the turbine blades. This improves energy transfer, turbine power, and overall plant efficiency while controlling the flow direction and minimizing energy losses. For the purpose, the nozzle in a gas turbine accelerates gases to a high velocity, maximizing kinetic energy transfer to the turbine blades. Its design ensures precise flow direction and velocity to improving turbine power output and efficiency by converting thermal energy into a mechanical energy effectively. So here are the 3 example problems at 3 different scenarios involving an adiabatic nozzle. In each case, we need to determine the exit velocity of the air. We treat air as an ideal gas and assume a steady flow process where heat transfer and work are at zero. Therefore, the decrease in enthalpy is converted directly into a kinetic energy. So from 3 different problems, we can solve in same solution. For an example, we can see all the given are stated in the question. According to the step 1, we need to calculate the enthalpy based on the value given. Step 2, find the temperature at the outlet using the isentropic relation for ideal gas. According to the step 3, we need to calculate the enthalpy. And the final step, we can see the exit velocity, how the variable shift across 3 problems. Device, diffuser. The function of diffuser in gas turbine to slow down the high velocity gases from turbine or combustion chamber. It's also converting kinetic energy into a pressure energy. It's expanding cross-section in increases static pressure. It's also to improve cycle efficiency and ensure smooth flow into the next stage, optimizing overall system performance. For purpose of diffuser in a gas turbine system to recover pressure from high velocity gases by slowing them down. So here are the 3 example problems at 3 different scenarios involving an adiabatic nozzle. In each case, we need to determine the exit velocity of the air. We treat air as an ideal gas and assume a steady flow process where heat transfer and work are at zero. Therefore, the decrease in enthalpy is converted directly into a kinetic energy. So from 3 different problems, we can solve in same solution. For an example, we can see all the given are stated in the question. According to the step 1, we need to calculate the enthalpy based on the value given. Step 2, find the temperature at the outlet using the isentropic relation for ideal gas. According to the step 3, we need to calculate the enthalpy. And the final step, we can see the exit velocity, how the variable shift across 3 problems.
So for this slide, I will present about the problem and the solution. So we have 3 problems for turbine. So the problem number 1 is in a vapor compression refrigerant system. We refer to the table R34A. Enter an expansion turbine at a pressure of 1 megapascal and a temperature of 100 Celsius and leave the turbine at 200 kilopascal. If the mass flow rate of the refrigerant is 0.05 kilogram and kinetic and potential energy change are negligible, determine the work output of the turbine. So the solution as a given, we got P in is 1 megapascal and temperature in is 100 and the P out is 200 kilopascal. And for the M dot, we got 0.05 kilogram per second, and we neglect key E and PE. So from the table, we got H in equal to 270 kilojoule per kilogram, and H out we got 250 kilojoule per kilogram. So for the work in, we got for the work turbine formula is H in minus H out. So after calculate, we got 1.0 kilowatt. Next, for the problem number 2, refrigerant are tended to expand adiabatically in a turbine from 1.2 megapascal and 70 Celsius to 300 kilopascal in air conditioning system. The turbine has an isentropic efficiency of 85% and the refrigerant mass flow rate is 0.08 kilogram per second. So to calculate the actual work output of the turbine. So for the solution, as a given, we got P in is 1.2 megapascal and the temperature in is 70 Celsius and the P out is 300 kilopascal. So for the efficiency, we got 85%, and for the M dot, we got 0.08 kilogram per second. So H in 265 kilojoule and H out is 240 kilojoule. So for the formula, H out actual equal to H in minus efficiency, and then multiply with H in minus H outs. And after calculate, we got 243.75 kilojoule. So formula for the work turbine or work in is M dot multiply with H in minus H out actual, and we got 0.08. And then after we calculate all, and the last answer is for W work turbine is 1.0 kilowatt. Next, for the problem number 3, for the turbine, so in a small air conditioning system, I refer to the table R34A, enter a turbine at 900 kilopascal and 50 Celsius for the temperature and leave at 250 kilopascal. The mass flow rate of the refrigerant is 0.1 kilogram per second, and the change in kinetic and potential energy are negligible. Determine the turbine power output given that the inlet and outlet enthalpy are 260 kilojoule and 240 kilojoule respectively. So for the solution, as a given, we got P in 900 kilopascal and the temperature is 50 Celsius. For the P out, we got 250 kilopascal, and for the M dot, we got 0.01 kilogram per second. For H in, we got 216 kilojoule per kilogram, and H out, we got 250 kilojoule per kilogram. And formula for the work turbine, we got M dot multiplied with H in minus H out, and for the work turbine, after we calculate, we got 2.0 kilowatt. So for this slide, I will present about the function and the purpose for the compressor. So the function for the compressor in a gas turbine combined cycle power plant draw in atmospheric air and compresses it to the pressure required for the efficient combustion. As air passes through successive flow compressor stage, its pressure and temperature increase due to the mechanical work from the turbine shaft. So the compressor is essential for maintaining stable airflow, enabling complete full combustion, supplying cooling air for the turbine component, and significantly influencing the power output and efficiency of the gas turbine. So next, for the purpose, in the combined cycle power plant, the compressor supply high pressure air for efficient fuel combustion by increasing air density and allow more oxygen to participate in the process, and this leads to higher combustion temperature and improved energy conversion efficiency. The compressor is direct coupled to the gas turbine via a common shaft and consume a significant portion of the turbine mechanical output, yet it is essential for ensuring continuous and stable gas turbine operation. So for this slide, I will present about the function and the purpose for the compressor. So the function for the compressor in a gas turbine combined cycle power plant draw in atmospheric air and compresses it to the pressure required for the efficient combustion. As air passes through successive flow compressor stage, its the pressure and temperature increase due to the mechanical work from the turbine shaft. The compressor is essential for maintaining stable airflow, enabling complete full combustion, supplying cooling air for the turbine component, and significantly influencing the power output and efficiency of the gas turbine. So, net for the purpose. In the combined cycle power plant, the compressor supply high pressure air for efficient fuel combustion by increasing air density and allow more oxygen to participate in the process. And this lead to higher combustion temperature and improved energy conversion efficiency. The compressor is direct coupled to the gas turbine via a common shaft and consume a significant portion of the turbine mechanical output. Yet it is essential for ensuring continuous and stable gas turbine operation.
Assalamualaikum and hello everyone. My name is Nur Batrusha binti Zulkifli. My metric number is CD240048. Today I will be presenting on the mixing chamber, focusing on its function, purpose and several thermodynamics problem related to steady flow open systems. The mixing chamber is an important component commonly found in air conditioning system, refrigeration system and gas turbine combined cycle power plants. The mixing chamber acts as a thermodynamic control volume where two or more fluid streams are combined under steady flow conditions. In a gas turbine combined cycle power plant, the mixing chamber combines compressed air and fuel to form a homogeneous working fluid with uniform temperature, pressure, velocity, and composition. This uniformity is essential to ensure stable combustion, efficient turbine performance, and protection of downstream components. From a thermodynamics perspective, the mixing chamber follows the conservation of mass and energy. It performs no mechanical work, but it plays a critical role in minimizing temperature gradients, preventing hotspot, and ensuring long-term operational reliability of the system. The main purpose of the mixing chamber is to ensure true and uniform mixing of fluid stream, such as fuel and compressed air under steady flow open system conditions. By producing a homogeneous mixture with consistent temperature and composition, the mixing chamber has the first one is prevent local hotspot, number two reduce thermal stresses, the third one is avoid material degradation and turbine blade failure. Although no work is done within the mixing chamber, energy transfer occurs primarily through enthalpy change. Proper design and operation of the mixing chamber enhance combustion, efficiency, system stability, and overall power plant performance and longevity. Let's look at how this applies to real-world calculation. In our first problem, we have an air conditioning system mixing two streams of air. Stream 1, we have 1.5 kg per second at 18 degrees Celsius. Stream 2, we have 0.5 kg per second at 40 degrees Celsius. The solution is, first, we apply the conservation of mass. The total outlet flow is simply the sum of the inlets. 1.5 plus 0.5 equal to 2.0 kg per second. Since Cp is constant and there is no heat transfer, we use the energy balance equation. m.1 multiplied by T1 plus m.2 multiplied by T2 and equal m.out multiply T out. Plugging in the number, we find the exit temperature is 23.5 degrees Celsius. Next, the problem 2 follows a similar logic but looks at a building fresh air intake mixing with return air. Outdoor air 0.8 kg per second at 35 degrees Celsius, return air 1.2 kg per second at 24 degrees Celsius. So the solution is our total mass flow is 2.0 kg per second. By applying the steady flow energy balance, we calculate the weight average of the temperatures. The result is comfortable 28.4 degrees Celsius, leaving the chamber. Finally, let's look at a refrigeration system. In this case, instead of temperature, we are working directly with specific enthalpy. Stream 1, we have 0.06 kg per second, and the enthalpy is 260 kJ per kilogram. Stream 2, we have 0.04 kg per second and the enthalpy is 300 kilojoule per kilogram. So the solution is the total mass flow is 0.10 kilogram per second. Using the energy equation, we use 0.06 multiplied by 260 plus 0.04 multiplied by 300 equal to 0.10 multiplied by H out. This gives us a final specific enthalpy of 276 kilojoule per kilogram. Next, I will explain the heat exchanger, focusing on its function and purpose in a combined cycle power plant. The heat exchanger plays a critical role in improving plant efficiency by recovering waste heat from gas turbine as house gases. In a combined cycle power plant, the heat exchanger, commonly known as the heat recovery steam generator or HRSG, operates as a steady flow open system. Its main function is to transfer thermal energy from the hot house gases leaving the gas turbine, typically at temperatures between 450 degrees Celsius and 600 degrees Celsius to the feed water. This process occurs without direct contact between the house gases and the water. As a result, the feed water is converted into high-pressure steam, which is then used to drive the steam turbine. The heat exchanger operates according to the first law of thermodynamics, where the energy lost by the house gases is equal to the energy gained by the water or steam with negligible losses and no shaft work. By regulating house gas temperature and recovering waste heat, the heat exchanger significantly enhances thermal efficiency, reduces fuel consumption, minimizes environmental impact, and allows the gas and steam turbine cycles to operate independently while working synergistically. The primary purpose of the heat exchanger in a combined cycle power plant is to recover and utilize waste heat that will otherwise be released into the atmosphere. By transferring this residual thermal energy to water, the heat exchanger produces high-pressure steam for the steam turbine, enabling the integration of the gas turbine and steam turbine cycles. Operating as a steady flow open system under the first law of thermodynamics, the heat exchanger ensures that the heat lost by the exhaust gases equals the heat gain by the working fluid with negligible shaft work involved. This process allows combined cycle power plants to achieve overall efficiencies of more than 55 to 60%, leading to improved energy conservation, reduced fuel usage, and lower environmental emissions. Next, we will explore 3 practical applications of steady flow heat transfer in thermal system. Our first case study focuses on a vapor compression refrigeration system using R134A as the refrigerant. System setup: refrigerant flows through an evaporator at a steady mass flow rate of 0.05 kg per second. Energy that it enters with a specific enthalpy of 250 kJ per kilogram and exits as a saturated vapor at 400 kJ per kilogram. The calculation is to find the rate of heat absorption Q dot evap. We multiply the mass flow rate by the change in enthalpy, which is Q dot evap equal M dot multiplied by H out minus H in. Result: applying the values, we get 0.05 multiplied by 400 equal 400 minus 250, resulting in a heat absorption rate of 7.5 kilowatt. Next, we move to the condenser of a refrigeration system where energy is rejected to the surroundings. Flow conditions: the refrigeration flows steadily at 0.08 kg per second. State change: it enters the condenser with a high enthalpy of 450 kJ per kilogram and is cooled to a saturated liquid at 280 kJ per kilogram. The calculation is the rate of the heat rejection Q dot condenser is calculated by M dot multiplied by H in minus H out. Result: by calculating 0.08 multiplied by 450 minus 280, we determine that the condenser rejects 13.6 kilowatt of heat. Finally, we look at an air conditioning application involving a cooling coil. Airflow data: airflow through the coil at a rate of 1.2 kg per second. Temperature differential: the air enters at 32 degrees Celsius and is cooled down to 18 degrees Celsius. Assumption: we assume the specific heat capacity Cp of air is constant at 1.005 kJ per kilogram Kelvin and neglect kinetic and potential energy change. The calculation, we using the formula Q dot equal to M dot multiply Cp and multiply T in minus T out. We calculate the heat removal rate. Result: this gives us 1.2 multiply by 1.005 and multiply 32 minus 18, which equals a heat removal rate of 16.9 kilowatt. That's all from me. Thank you.
So the conclusion for our group project is, through a detailed assessment of 7 essential steady flow devices, this project demonstrates how the first law of thermodynamics governs the corpus energy transformation required to maximize thermal efficiency in a combined cycle power plant. The analysis revealed that overall plant performance is highly sensitive to individual components' efficiency, particularly highlighting how multi-stage compression with intercooling minimizes peristaltic power by approaching the isothermal ideal. Ultimately, the transition in a combined cycle illustrates a masterpiece of thermodynamic optimization, independent open system into a highly efficiency integrated power generation network. Thank you.